Okay, so in geometry class, when you begin to learn about angles, okay, Angie's, yes, angles, when we draw them, we kind of draw them kind of wherever and floating around in space. So let's begin by talking about drawing. Um, well, first of all, I should use blue. Second of all, okay, drawing angles. Angie, look at that L. Yes, there it is right there for you guys. Okay. In geometry class, it begins with this little dot, which we call vertex. Not a big deal. And then we call this thing a ray. So it begins with this idea of a vertex, and then we have our initial ray. Okay? Now, the angle is created by the other ray that's joined with the same vertex. And the space between is what we call an angle, and I'm going to use theta to sort of dictate that there's an angle being drawn, and that's the one I'm referring to, versus the angle going the other way on the outside. It's customary when we talk about trig and we're drawing angles that we use an arrow to indicate the initial side, which is the one that I've drawn first, and the terminal side, which is the one that I have drawn second. So this is called the terminal side. So far, so good? Okay with that? Well, the problem arises when, how do we then guarantee that when you draw a 45-degree angle and I draw a 45-degree angle, that our angles look the same on the page, right? 45 degrees is 45 degrees no matter how you do it, but we want to be able to measure 45 degrees from a location. So what we do is we learn how to draw angles in standard position in a trig and pre-calc class from here on up. So in geometry, you just kind of drew angles wherever, learned how to draw them. In this class, we learned how to draw them in standard position, and that brings us to the second idea. So we're going to talk about angles in standard position. Yep, here we go. To draw an angle in standard position, we first draw a coordinate plane. Okay, and everyone's very familiar with the coordinate plane. It has the x and the y axis. That's our first idea. We start with that. I'm going to move up just a little bit so you can all see. Second thing we do, if you had to take a guess, where do you think we would glue the vertex down on the coordinate plane? If you just had to take a guess. At the origin, 0, 0. Yes, not negative 5, 3. That would be terrible. We instead just do it right here, and we glue the vertex down at the origin. So the origin becomes our vertex. And that's a very good guess. Now, I have two rays that I'm working with. I have an initial ray, and I have a terminal ray. Well, one of those rays, we're going to glue down somewhere so we hold it in a fixed position so it never moves. If you had to take a guess, the x-axis. But which side of the x-axis? Right. The positive side of the x-axis. So we're going to glue down the initial side of our angle to the positive x-axis. This is what it means to draw an angle in standard position. All right? The initial ray is glued on top of the x-axis, the positive side, and it never moves. Therefore, that leaves the terminal side able to swing around, right? Well, it can swing in two directions. It can swing up, or it could swing down, right? That's how we denote positive and negative angles, okay? So as an example, if I were to draw this angle here, indicated by that arrow, this angle theta is what we would call a positive angle. Okay? Positive angles swing which way in terms of a clock? No, counterclockwise. Positive angles swing counterclockwise. Why do you suppose that this is?
Because you have the line here.
It has something to do with the quadrants, right? This is quadrant 1. This is quadrant number 2, right? This is quadrant number 3, okay? And this is quadrant number 4. So it follows the quadrants. So 1, 2, 3, 4. So positive all the way around, okay? Now, if I want to draw a negative angle, well, then in standard position, the vertex would still be glued at the origin. The initial side would still be glued to the positive x-axis. And if I swung down this way, and I called this angle beta, This angle beta would be a negative angle. What's that? There's no difference between theta and beta. They're just names that we give to angles, right? They're like variables. X, Y, Z, Q, R. They're just the variables that we denote angles by. No, you don't always use. There's no standard one to use for anything. You just sort of use whatever you want. Theta, beta, alpha. These are all pretty straightforward or commonly used notations for angles. Okay. All right. So positive angles swing which way? Yes, counterclockwise. Someone write that down here. So positive angles are counterclockwise. And negative angles are what, you guys? Clockwise. Very good. Okay, as an example, here's what I'd like you to do. I would like you to draw for me an angle of pi over 3 in standard position. Pi over 3 in standard position. Draw that for me right now as an example. Okay, that right there is an angle of pi over 3 in standard position. It's a 60-degree angle, so it should look pretty close to a 60-degree angle. It should definitely be in quadrant 1, and it should be more than 30 and more than 45 degrees. Fair enough? Okay, here's the next task for me. Draw for me negative pi over 4 radians, negative pi over 4 radians in standard position. Please do that right now. Okay, negative pi over 4, you should have a drawing that looks like this. This right here, this angle, I'll call beta for now. This is negative pi over 4, right? It should look just like that. And the cool thing about standard position is that we all have the same picture when we're done. So we're not just drawing random angles floating around in space. They're glued to a coordinate plane, okay? Okay, last one. Everybody, please draw negative 3 pi over 2. Draw negative 3 pi over 2. So negative 3 pi over 2, I'll use orange for this one. So here's what negative 3 pi over 2, oh, that's still green, sorry. Let's use orange or red or whatever I got. So here we go is my initial side. So, and look, it's like this, right? But how do I dictate the fact that that's not just regular pi over 2, right? I draw the arrow here. So alpha is negative 3 pi over 2. Hey, is it possible to draw an angle that's more than 2 pi? Yeah, it sure is. Can you guys draw me an angle of 4 pi? Oh. Here, I'll move over, okay?
You have to like circle twice.
Yeah, but how? How do we do it? Okay?
Circle.
One small one and one big one.
You make a spiral, okay? So here's 4 pi. I'll show you. Here's 4 pi, okay? If I go all the way around once, that's 2 pi. Go around twice. That right there, that's an angle of 4 pi. And yes, that's how you draw it. And yes, we're allowed to do that. All right, we're going to talk about arc length, but we're going to come at the arc length formula from a radians perspective, okay? From a radians perspective. In your geometry class, you did learn an arc length formula. Remember what it was?
Yeah.
No.
What is it?
Central angle is equal to the arc length.
Yeah, the central angle is, but I'm talking about arc length is the distance along the edge of that circle, right? Yeah, what is,
Wait to find it.
yeah, like what? Do you remember what it was?
Yeah.
What is it?
Isn't it up? Oh wait, no, I just did it like with the angle of degree and radius.
Well, I want to show you how this works, where this comes from. Please draw a circle, best you can. Okay. Every single circle has a radius. Now, remember, we're coming at this from a radians perspective, okay? From a radians perspective. So what I'm going to do, right, is I'm going to draw for us exactly 1 radian. So that means that this length right here is r, correct?
Yeah.
Okay, that means I have created an angle here, which I'll call theta for right now, all right? So theta, right, is equal to, right? It's equal to this r value I have over my radius, okay? Which is the same thing as 1 radian. Of course it is. That's the definition of a radian, right? It's equal to a radian. So theta is equal to r over r, which gives me exactly 1 radian. That's the definition of a radian. You guys agree with that? You guys with me?
Yeah.
Okay. Now, let's just extend this a little bit, okay? Let's say that I draw another one here, and I go another radius along the edge of my circle. So I'm going to call this angle over here, this big blue angle, I'm going to call that an alpha. All right? Well, then alpha is equal to not 1r. How many r's do I have along the outside of my circle? I have 2r's. So 2r divided by r gives me exactly 2 radians. You guys agree with this part? Yeah, so with me on this? Yeah, okay, because the r's would cancel, give me 2 radians, right? 2 radians. All right, let's do it one more time to drive the point home here. Let's do purple. Okay, if I did like here and I called this an r, then this purple angle here, which I'll just call beta for now, all right? Then let's follow the same pattern. Beta would have to be, how far have we gone around the edge of the circle? 3 r's, right? 3 r's to give me exactly 3 radians. You guys agree with that part? You guys still with me on this? Okay. So, remember, we're coming at this from a radians perspective. So that means, in general, let's say if I just kept going with this, let's say then, for example, I didn't land on exactly an even integer multiple, or any integer multiple of r. Let's say that I'm just curious as to, I just want to find this length right here, which is this green arc. Okay? I just want that. Well, and I'm looking for this angle that's represented by that. Well, what's the relationship here? Well, I'm going to call this, for the moment, that length, the green length S. Right? So what do I do? Right? The S is equal, or sorry, I'll start from my theta. The theta value, or I shouldn't use theta because I already used theta. Which one haven't I used yet?
Delta.
Oh, delta. I haven't used delta. Okay. So delta, so this angle here, let's just call it delta. So this angle here, delta, if I follow the exact same pattern that I've been using every single time, then it's going to be no different, right? It's going to be the length that I have denoted this as green, right, is S divided by what? R. There it is. And that's going to be radians. That's how I get that angle out of it. It's just S over R. So in general, the point I'm trying to make...
1 radian.
No, whatever, the angle is that radians, yeah. So in general, the point I'm trying to make here is that any angle that we create, and this is called the arc length formula, is nothing more than the length of the arc divided by r. Okay? But remember, this is measured in radians. Okay? So another way to represent this formula, a way that most people represent this formula, is this. The arc length S is just equal to r theta. But again, this only works if what? If theta is in, what's the word, you guys? Radians. Alright? This only works if theta is in radians. It's very, very important. Okay? And that's kind of the development, or the thinking, coming at it from a radians perspective. Okay, give yourself a circle, and let's say, you guys ever seen those, like, vinyl records? Those record players, right? Let's say you have a 10-inch vinyl record, all right? And what you do is you put a little tiny sticker on the edge of that vinyl record, right? And you spin that vinyl record through a degree of 120 degrees. 120 degrees. So not all the way around, just 120 degrees. Okay, the question then is, what is the distance that little tiny dot on the record has traveled? What's that linear distance, right? Okay. So what we're going to do is we're going to use the arc length formula. So we're going to say S is equal to R times theta. Very, very important idea. S is R theta. So S, which is called the distance, the arc length, is the radius, which is 10, times my angle, which is 120 degrees. How come no one's stopping yelling at me? Nick, what's the deal? Has to be in radians, so I have to multiply. I have to convert this. I have to take my degree, convert it to a radian. We do that by multiplying by pi over 180, which is what Nick was saying earlier. Okay, so therefore S is now equal to 10 times, 120 degrees. We did that one earlier in the class. We found that that's just how many radians? That's 2 pi over 3 radians. Therefore, the arc length is 20 pi over 3 inches. And when you calculate that out, that's approximately 20.95 4 inches. So that dot has traveled a length of 20.94 inches, okay? The most common error, students forget to do this part and forget to get the radian part there. The conversion. All right, I have some Latin students in here. Co-terminal. What does that mean? What does that word mean? Co-terminal. Two terminal? Shared terminal. Co means with, right? The Latin word for with. So, okay, with the same kind of thing. So, co-terminal angles, it literally is what it says. So here's the definition I'm going to give you. Co-terminal angles is nothing more than this. It's nothing more than two angles with the same terminal side. Yeah, right? It's exactly what it says. The same terminal side. Now, if our angles are in standard position, they'll also have the same what? Initial side, right? Because it's glued down to the positive x-axis, right? So coterminal angles are two angles with the same terminal side. Okay, why am I introducing this to you? Here's why I'm doing this to you, right? Let me give you an example right now to illustrate the point, all right? I'm going to give you an angle of theta that's equal to 3 pi over 4, all right? So here is an angle, theta, that's equal to 3 pi over 4. It's in the second quadrant, right? It's 45 degrees in the second quadrant. Okay, now, what if I wanted to get to this location in a different way? What if I wanted to go that way?
Oh, you minus the whole thing. 360.
3 pi over 4, yeah, 3 pi over 4, okay? Well, what if I wanted to get to that angle a different way? How would I do it? How would I get, like, let's call this angle, green, right?
Pi over 180 minus.
So let's call this beta. Well, beta would have to equal, well, what did I do? Well, I started at the angle that I was at, which was 3 pi over 4, right? If I start here and I go all the way back around, I'm just subtracting off how much? A full rotation, which would be?
Pi over 180.
No, 2 pi. Thank you, Julia. That's exactly right. This is why it's important to know how to add and subtract fractions. So, no. Let's stay in radians. Stay in radians. Okay, look. This is just 3 pi over 4 minus this is 8 pi over 4. Oh, good little trick there. So that's negative 5 pi over 4. Okay, interpret this with me. Here's what I mean. If I wanted to start here and I wanted to draw the angle of negative 5 pi over 4, I'm going to end up in the same place as if I drew the angle 3 pi over 4. Watch. All I do is count, right? This is negative 1 pi over 4, negative 2 pi over 4, negative 3 pi over 4, negative 4 pi over 4. Oh, negative 5 pi over 4. So, negative 5 pi over 4 and 3 pi over 4 are an example of angles that are coterminal because they share the same terminal side. Another point. I want to find another one. I'm really interested in another one. So look, if I start at 3 pi over 4, if I start with this, I want to go around another 2 pi to get to the same spot. So I would add another 2 pi, which is just 3 pi over 4 plus, there's that 8 pi over 4 again, which is just what? 11 pi over 4. Oh my gosh. So look, all of these angles, 11 pi over 4, negative 5 pi over 4, 3 pi over 4, these are all called coterminal because they end up in the same terminal spot. Okay? James, question for you.